And we will move for the third presentation, which is focused on the automation for fuel inspection processing. Let me introduce the next speaker, Mr. Marcin Kopec. He is working in a research center since 2015. He works, or he's involved in the fuel inspections at the Temelin power plant. He's involved also in the development of new tools for processing of data from the inspections, not only to be applied for the Temelin, but also for other applications. So, place is yours.
Thank you very much, Mr. Chairman, for the introduction. Ladies and gentlemen, I would like you to show you something different, maybe what you have seen so far today. Once for the matter of the interest, so I will speak about nuclear fuel, but also in the matter of what we are doing and what we apply to process the data. Just like as the introduction, I will speak about also AI, which is really fancy word nowadays, but it's not direct AI, because what is AI right now, but it's more computer vision. And in my presentation you will see two main, let's say, scopes of our work. One I will mention right now, and then I will go back to this. This is synthetic data, because the data from the power plants are mostly under some regulations, so we are not able to, I don't know, open this, publish this, or to process this in open source codes, open source, let's say, engines. That's why we have developed our own let's say, tool for synthetic data production. You will see some parts of this, and I will go back for this to this topic further in the presentation. But first of all, I would like to, let's say, conduct a small social experiment on you. I know that we don't have time to, let's say, evaluate then the experiment, but just take a look on those short videos. They are mostly more or less the same, about the same topic, but the most important part is that when I will ask you right now in which exact second the blue ball appeared on each of those videos, some of you may answer this question right away. Some of you will need to re-see those videos once, twice, maybe 5 times, just to know the perfect timing. And basically here we can start the whole story, which is about digital image processing, because you don't need to watch the videos once and then and again and again and again, because you have some better things to do during this time. Just to start about the fuel and how we use the digital image processing, some small information about the motivation and background. More or less the fuel assembly is something which is like 4 meters long. I know that I maybe shouldn't tell you what is fuel, nuclear fuel, but just to have all information in our hands. The area of interest in our case when we are doing the fuel inspections is a couple of millimeters or smaller. We have like 10 minutes video for one side of the fuel assembly. In case of mentioned Temelin nuclear power plant, there is hexagonal fuel, VVR fuel. So 1 hour for the whole fuel assembly, and in case of PWR assemblies, as you can see here in the picture, it's, let's say, 40 minutes. The image processing does not only process the video, it helps us to visualize what we need to see, so it makes more readable what is inside the video and inside the fuel assembly, basically. We can, let's say, automate the routine tasks. So if everything is okay, we can say that 75% of the fuel inspection video is, let's say, not so important and maybe sometimes boring for people who are not performing fuel inspections, but the leftover 25% is what we basically are focused on, where some anomalies appear, and digital image processing helps us to find those places and to trace all the issues, basically what you can see in the fuel assembly. Our, let's say, history with fuel inspections dates back to 2011. There are also in here some people who started the fuel inspection done by CDR at Temelín power plant. Since 2023, there is new. Since 2021, there is new fuel inspection equipment, which you can see on the photo. It's like 3 sites at once taken at the video, so we don't have too much time to think of what we are seeing there. That's why we started, like in 2018-19, we started to think about some kind of digital assistant that will use all or some of parts, what right now we can call AI, to help us to find some more inside of this videos from the fuel inspection. And since 2023, we also started to cooperate with not only Temelín, but other fuel vendors and fuel inspection companies. But what basically the fuel inspection provides for us, it's mainly safety. So we need to know that our fuel behaves safety according to the design criteria, according to what is typical for this type of fuel. And as you can remember those 3 videos, please take them at the beginning, please take them like 3 different types of fuel. So basically similar, but quite different. We somehow also need to minimize some operation risks that are followed with costs on something like this. We just need to know how this fuel behaves after some time spent in the power reactor. All of this is done basically underwater. And we are not able to touch the fuel in any means, so we just need to take out everything what we need just from this video. So if we are just having our eyes, it should be enough, but there are dozens of tons of gigabytes of those videos, and you need to basically sit and screen this. And for example, you sometimes are, I don't know, tired of something, and you may not see everything. It's not typical and normal, but still, if you have a lot of those videos, you need to be prepared. You need to be sure that your work is done perfectly and you are not neglected anything. That's why we also were thinking about this digital assistant for us. In this case, we can decrease the workload on the critical path, so we can increase the numbers of the videos because we do not need to be focused directly at the power plant. I mean, in this case, for Temelín site, where we have VVR type, so everything is done basically on the critical path. But also we can increase the information load and the data flow in case where you have a fuel building, and basically you can inspect this video whole year long. The optimization, as I mentioned, is based mainly on machine learning and some AI tools. The workflow, as you can see, is that we need to provide the acquisition of the videos, sometimes from the 4 cameras, from 3 cameras, or from 1 camera. It does not matter, basically, because we are able to process more and more. Then we need to extract all data from this video, so process the data. We have some criterion, some parameters we need to follow. That's why we are taking a look on those process data on those specific parameters. Then we are able for sure to create the airports, and as we know, we want to go back to some videos, we need to store them. And if in case, I know that this is like a trivial point, but basically when you have like 300 megabytes of video, we can comprise this to, let's say, 30 megabytes without any loss of the context, any loss on the precision, and any loss of the of all the information inside this video. So just to have like this in a graph, all of this basically with the tracing of the trends provides us knowledge, and basically we are able to do our job in a better way. The most important part of this software is something what we call one image overview. This is basically transition from the time domain into a spatial domain. So we no longer work with videos, we work with one big image that comprise everything what the video has. No contrast loss, no data loss, no resolution loss. Everything is basically there inside. What you can see inside the video is basically then seen in the OIO. OIO, when you, let's say, apply some math look on this, is like a matrix of a lot of layers connected to each other and basically screen through each other, and then you can see everything what is inside the video. For sure, it provides you a faster overview. It is fully zoomable, and basically with your computer you don't need so much graphic power and so on. You can place all those videos next to each other, and you can compare in a better way, so tracing also the trends from year to year when you have the same fuel inspected twice or 3 times or whatever. And basically you can apply these really easy tools for any kind of annotation. So you can basically go back like what happened with this fuel 10 years ago, and you have everything inside the image, not in the video or any kind of reports. So the main feature is basically taking the videos and then preparing a map of OIOs out of this, and I will strengthen this once again: no context loss on all of those images. I think that now I can say that you may see already some other usage of this technology, yes, and at the end of my presentation I will show you also some different, let's say, prototypes or tools we have right now based on this technology. But when we were thinking about this, that we have already some algorithms performing what we want, so we started to create also like something what we can call a software, more or less. There where the operator or the power plant can plug to any kind of station, more or less any kind of station, and then you can basically process the videos in an automatic way. So at the end of the fuel screening, fuel inspection, you have most of data pre-prepared for further evaluation of the operator, of the inspector of the fuel, basically the expert who takes the responsibility for this. And this is also to be strengthened. It is not to replace the human force that claims the responsibility for the outputs, but it's just to help the people not to overwork themselves, but to have time to do this job better. The output quality of the photos of the OIO is basically related to couple of parameters. You can see them in here. Our idea is just to lower the parameters that you require to see something because of the due to the implementation of the layers. So you can take some information from, let's say, angle point of view on the fuel, and you can take some information from another light exposure and so on. We can basically extract this from this video because all colors of lights are inside the white light. We use this. All angles you can see on each frame. And when we combine this, we can even, let's say, get to the point where one pixel on the camera represents something which is like 0.05 millimeter big. So really small changes or anomalies are also possible to be visible on the image. Then what I mentioned before, when you want to compare this, we have our part of our software looks like, let's say, this. You can place all those OIOs next to each other, and here you can see at the bottom. I don't know, is this working or not? So at the upper part, we can hear some labels, so you can choose the point of view from which we are looking on the fuel. And for example, it is perfect tool for scratches, because when you see some scratches on the fuel or something similar, you can have really angle point of view on the fuel, and then it is bright, very bright for you just to trace those marks. But still, you can use this tool for different fuels, for the same fuel and at different age, and you can basically compare, for example, if this kind of anomaly is growing or is decreasing or anything what you can imagine. Also, for example, for tracking of the oxide layer on the fuel rods. But what we right now need, or what we were working for last couple of months, is this tool. It's our portable server. We are able to go to any power plant and plug there the cameras, either digital or analog, and process the images and the videos on site. So, for example, when you imagine that there is, I don't know, there will be new power plant here at Dukovany or in Poland, we go there, we take those videos, and we are able to prepare the report right away after the end of the inspections. This situation took already place in Finland, and 4 hours after the finishing of the fuel inspections, we were able to provide the reports from our side. But OIO is just like a matrix for a lot of different things. So basically the potentials that OIO has is also, you can see also on this slide. We are able to measure fuel geometry, we are able to measure rod geometry, we are able to trace any, let's say, foreign objects like you see on the right bottom corner. We are able to segment any, let's say, component of the fuel out of the video and compare this, for example, with whatever you want. We can we can perform some special video automatic cutout. So, for example, you are only interested in the upper part of the fuel. I don't know why, but let's say, and then we can automatically process this, and you don't need to have whole video. And of course, we are working of everything which is visible in the video, so also the fuel geometry can be, let's say, the whole fuel geometry, fuel assembly geometry can be compared between each other. Oxidation map, this is something what we have on another slide. I will show you right away. And basically this is also something that can be extracted directly from the image, from the video. Fuel assembly bow, this is one of the oldest tools we have. Basically we are able to extract this directly from the image. That's why I was mentioning about this. And here you can see the comparison of our method with typical method used at Temelin site a couple years ago. It is not directly taken from the power plant, but we cross this method with our algorithm, and those, let's say, you maybe cannot see this, but our vector is basically the same like those two pink ones. There are actually 3 vectors, and our is just in the middle of this. Then you can have the projectile of each side of the fuel assembly, and you have this onion on the right side, just to show you how the fuel, how each face of the fuel assembly is projected towards the camera. Of course, including camera lean or any shaking, any bowing of the twisting of the fuel assembly. We can, let's say, eliminate this harm out of those data, and that's why we are able basically to store the whole projection of the fuel assembly bow in a number and no longer in a form of video. Another, let's say, tool that is able to take out from OIO is basically the rod growth. Right now we have checked this on our data from the power plant. We are somewhere in like 98% of accuracy. The leftover 2% the operator is able to, let's say, improve in our graphic user interface. So you acquire 100% of accuracy in this case. As I mentioned, and I will strengthen this once again, we are not to substitute any expert in this whole chain, but just to help the expert to be focused on the work she must do and not to rewind the videos. The follow-ups that we want to develop in the future, basically this oxidation map on the left side is already ongoing and really nice looking. So next year I think that we have like a perfect tool for this. But we can recognize the oxide layer. We can extract the whole map of the oxides, and basically we can somehow classify them into 2, 3, 4 classes. Whatever you want, basically, we can work with this. Also, extract this oxide layer map and place it on another video or another data. Why? Because all the data you have seen so far, including those ones, are made from synthetic fuel assembly. So all the images you have seen so far are basically done. Cut it out from the artificial data, so the data we can put to our AI engines and AI models, and just to verify if everything is working okay. And then after this, after we have like a closed, not open model, we can use this for the data on the power plant. Just like a small summary, what we are right now are able of, those 2 images are not, of course, from the synthetic data. This is from our laboratory. We put there everything what we can imagine of, and then we try to find all the objects and find all the problems, including fuel rods. And basically, our tools are able to perform something like you can see here. Just like a very future and very promising work is the remote complex analysis. The fact that we introduced portable server is not cut it out from the cybersecurity. In our, let's say, chain, we would like to achieve something like you can see in here. So we have encrypted data. We even that are processing the data, we don't know what is inside. Then the data are processed and also encrypted and put it back to the to somebody who basically ordered this. So, for example, the utility, and we are able to store this in a classified and certified data storage that is closed for everybody who is not entitled to go there and to see this. So we are not neglecting also the cybersecurity in our processing chain. Some references, mostly as you can see, Temelin site here in the Czech Republic, but also Gisgen and oil-free. So we already proved that our tools can be used and basically are working as they should. I have here another, let's say, slide about our publications and basically our articles. You can, let's say, Google. Sorry for this, but I would like to skip to something else. As I mentioned, so the digital image processing is not only that we, let's say, develop in here. It's not only used for the fuel assemblies, but also for other principles. This is okay. Very shortly, this is basically the tool you will be able to see today. This is for threaded holes. We go inside, we have this video, and then we perform the OIO, and then we can evaluate the defects inside the threads. Another tool similar to this, we have some specimens of biological shredding. We can have the video, then we can process this, and then we can extract all the cracks and all the, let's say, inhomogeneities inside the surface layer. And crossing this with some ultrasonic testing, which is now pending in our projects, we are able to say what is inside these specimens. And from my side, this is everything. Thank you very much for your attention.
Thank you for your very comprehensive overview.
Sorry for being, let's say, too long in this.
One question, if there is, because we are a little out of schedule. If not, we will skip the questions and we will move for the last presentation of this section, which will be presented by Dr. Daniel Dopiela. Its topic is a machine learning application in ultrasonic testing of welds, and Dr. Dopiela earned a PhD in mechanical engineering. He began his career at ATG Slovakia as an NDT technician and instructor of ultrasonic testing. Since 2017, he has worked as an NDT Level 3 expert at UJV, specializing in ultrasonic testing of critical components and contributing to national and international NDT projects. So, place is yours.
Thank you for introduction. So, my name is Daniel Dopiela, and I would like to present my topic, machine learning application in ultrasonic testing of weld. I'm sure everybody is looking forward to lunch, but I hope you have still enough energy for my presentation. So, I will briefly inform you about our national project. UJV is leading this national project. There are two participants. One of them is UJV and University of West Bohemia in Pilsen. Project started in January 2023 and it will end this December 2025. So, main objective was to develop some technology for evaluation of flows. I will use the term flows, but as you know, ISO standards, they recognize also terms like defects. So flows, they are equal to defects during the ultrasonic testing. And we are focusing on phase array technique. And of course, main objective was develop some, let's say, tool or machine learning, which can be used also for evaluation of ultravision data files. And we used our available phase array equipment. That means zircon unit, ultravision software, some scanners, phase array probes, and more. It was already said in previous panel discussion, there is like ENIC. ENIC means European Network for Inspection and Qualification. And there already is one document, or recommended practice number 13. And you can use this document like guide or manual how you can qualify machine learning at nuclear power plants. There are some basics about the deep learning, machine learning, and artificial intelligence. I would like to briefly inform you, or show you how phase array technique works, why we choose phase array over the conventional ultrasonic testing. Main reason is the phase array probe has several elements. We call it elements, but they are like transmitter receivers. So we can change the focal law and we can change the final UT wave, we can focus that wave, or we can change angle of that wave. So there are, on the market, there are phase array probe which can have 64 and more elements now. Main advantage of the phase array technique over the conventional ultrasonic technique is that we can see like three-dimensional view into weld. That means we can have more than one view. It's called top, side, and end view. And ultravision softwares like ultravision can merge these views into one UV data file. So NDT personnel can have more information about weld geometry, some relevant indications, can have more information about complex well geometry. For our project, we choose several test pieces or mockups. Chess company has several mockups which represent some critical components at nuclear power plants. This is only one example. We choose this mockup because there are two real cracks, R6 and R10. We use available phase array equipment like zircon unit, ultravision software, phase array probes, withdrawal frequency, and we use the same NDC procedure like at power plants. And this is the result. If there is some NDT personnel, NDT personnel should know what that means. We can see top, side, and end view of the well. This is the DM weld. There are several defects or flaws. That red areas represent flaws, and there are two real cracks in the root of the weld or in the heat-affected zone of the weld. And you can see also, it's called weld overlay, so you can see the geometry of the weld or of the pipe, but it's only theoretical geometry, because in the real part you can have total different geometry of the weld. For our project, we are also using the special tool developed by EPRI. This tool can, we can use this tool to modify ultravision data file. That means I can define, like user, I can define the volume in the data file, and after that I can make some changes in the data file. So I can change the flow, I can delete the flow, I can change the size, position, height, and more. I can change also amplitude of the flow. And for this purpose, I have to write, it's called configuration file. I will show you one example. This is the same data like on previous slide. So we have several indications, relevant indications from the flows, and I mark all of them in some, we call it like boxes. And after that, I can delete all flows from the data file. That means there is no limitation how can we use this tool. So I can have unlimited, we call it virtual mockups or virtual flow, and I can use them for machine learning. Main task of University of West Bohemia was develop some update of this tool from EPRI. They developed, I will call it virtual tool. That means user like me, I can define only a range of changes. So I can define like range of the size of the correct, for example, and that tool can produce hundreds or thousands variation of the correct in just minutes. It depends only on the hardware. This is the one example. That tool from, that update from university can produce hundreds variations in minutes, and we use this approach to train the machine or machine learning to train our tool for assisted AI in phase array technique. There is no limitation on variation of in flight size, flow size, position type, amplitude, and that's it. Okay. This is only basic overview how we approach to train neural network. We use the same ultravision data files. There was some like data labeling, positive samples and negative samples. It was made by UT level 3, of course. And after that, we use the samples for training neural network for our tool neural network. This was main task of University of West Bohemia, and our main task was test this AI or assisted AI. I will always say assisted AI because I don't believe there will be fully autonomous AI in at nuclear power plants. There should be always some final decision from the NDT personnel, and I choose only one example. I created new virtual mockup for that AI. This is the visualization of AI, how AI can see the indication in the ultravision data. And I don't know if you can see it, there are some dots, and the confidence scale for a positive response decision in one of the UV data test is highlighted in color. That means the maximum value at each location is always shown as projection, top and side view. This is only the comparison between AI and data file. So how you can see there is match between location of flaws and findings from the AI or assisted AI. And this is our next step, where we want to implement our tool or machine learning module into data acquisition. So we can take the same entity procedure. There will be data acquisition with the same equipment, zircon unit, phasor array probe, scanners, robot. And after that, our assisted AI can analyze final data from ultravision software. But I will say it again, there will be always final decision from the NDT personnel, and NDT personnel can log on that report generated by the AI. And this is our D-Day. There is no special about it. There is some scanner on the pipe, on the physical mock-up, dual phasor array probe with low frequency, and NDT personnel. We use the same zircon unit, and after that, we find one bigger problem, and that was electrical noise. This noise comes from encoders of the scanner, but colleagues from the university, they adjust the scanner, and after adjustment, this noise was lower, but it's still there. But next week we will have next data acquisition, and I hope there will be no noise anymore. But you still can see some electrical noise in this data. It's not too bad, but there shouldn't be any electrical noise from equipment. And this is our final result. This is only example of how can our assisted AI mark every indication in the data file. So there can be some red box which surrounding the indication, and after that NDT personnel can look at them and say, hey, this is relevant indication, this is not relevant indication, and make final decision. What can be next? We can use this data also for personal qualification, because we don't have any limitation in producing of virtual mockups or virtual flows. And we can use also for this other document from ENIC or RP10. And this document allows us to use the virtual flows or virtual mockups, test pieces for qualification of NDT personnel. And why we are doing this? Because physical mockups, they are so expensive, they are too difficult to manufacture, and there can be alternative like virtual flows or virtual mockup. So thank you for your attention, and that is all for me for now.
Thank you for your presentation. Because of the time, we will skip the questions and answers, because you are a member of a panelist so there will be possibility to ask you during the panel session. So at the moment, I would like to ask the panelists to come down and to be able to participate in the panel session, which will be moderated by Mr. Palmares. So I will pass the micro to him for the chairing of this panel session.
Okay. Good morning, everyone, again. I would like to welcome to our panel discussion. We will be focused to NDT, maybe to the future of NDT, some trends, challenges, and innovations. Firstly, I would like to introduce my panelists. First one, Bohuslav Kolář. He was introductive during his presentation. The second one, Daniel Dopěra. You also hear his introduction. The third one is my colleague from Research Center Řeš, Mrs. Jana Veselá. And she graduated in West Bohemia University in Pilsen, Faculty of Mechanical Engineering, in Department of Materials and Metallurgy. Since then, he has been working at manufacturer of generators, formerly Škoda Energo, now Brush-Sem, and since 2017, she has been in Research Center Řeš as an NDT expert. And the fourth one is Mr. Eusando from an engineering corporation. He is starting in Kepco KPS in the year of 1986, which is responsible for maintenance and inspection of inspections of all nuclear power plants and thermal plants in Korea as partially government-owned company. He has participated in Westinghouse company training course for NDE and in-service inspections engineering from the year of 1995 for 1 year. He has been performing many in-service and pre-service inspections of nuclear plant in Korea and United Arab Emirates for manual examination and automatic mechanized examinations for 30 years as level 3. In-service inspection engineer and project manager. He's working for Cyan Engineering Company as an in-service inspection vendor in Korea now. He is a member of a code committee for KEPIC. It's a Korean electric power industry code, similar to ASME code in Korea from year of 2010. Firstly, I would like to introduce my panel discussion. What will be the topic? Why is this topic, NDT topic, is so important? So non-destructive testing is more than just a quality control tool. It is a cornerstone of safety, reliability, and efficiency across industries, from aerospace and energy to manufacturing and infrastructure. When NDT fails, the consequences can be catastrophic, like equipment failures, financial losses, and even risks to human lives. Today, this field is undergoing a major transformation. Traditional methods like ultrasonic and radiographic testing are being complemented and in some cases disrupted by digitalization, automation, and artificial intelligence, like you saw in previous presentations. And we are moving from manual inspection to robotic systems and predictive analytics. This shift brings incredible opportunities, but also new challenges, compliance with evolving standards, cybersecurity of inspection data, and the need for highly skilled professionals. Why does it matter? Because the decisions we make today will shape the future of safety and innovation of critical sectors. Our goal in this session is not just to share facts, but to spark a conversation about where NDT is heading, what obstacles we face, and how we can collaborate to overcome them. So I think we have outstanding panel of experts who bring diverse perspectives from technology development to practical implementation. But before we start the discussion, I will a little bit have your attention. So if you could please your smartphones and scan this QR code. I have a little small survey, small poll for you. And the question for this poll is, which NDT method is your favorite? And during the time where you answer the questions, maybe I would like to ask each panelist for his answer to this. Maybe I could, I will show you the.
Oh, come on, someone put their X-ray, you know.
Okay. I have only basic method here, not the special techniques, but Daniel?
My favorite NDT method is, of course, UT.
Okay, thank you. Jana?
The same, UT, but I use visual examination or inspection as a standard process of all NDT methods.
Okay.
Yeah, I think the UT is best, and the next, I think, eddy current.
Okay, thank you very much. So little seconds. So I think that UT is the winner, but VT is very close. Okay. Thank you very much. So UT is the winner. For me, it's a good answer because I'm also UT guy. So I prepared some questions for my panelists. So first question is, where do you see the use of modern NDT techniques and methods? Where do you see the benefits and challenges based on your experience? So I have here, for example, some special techniques for different methods, but you could answer from your opinion, from your point of view.
Okay. Hi everyone again. Well, I will start with the benefits of these actually advanced methods or advanced techniques. Well, for the first main benefit is that it's quite visible right now that we are gaining lots of data using even standards technique and we have lots of information in the data, but we are not able to decode the information from the data. And the best benefits of these new techniques, UT or RT, whatever, is that they are working with the data and they are decoding more and more information from the data we currently have. That's really great benefit. The challenge is, well, all these new methods needs lots of equipment to work with. Because, you know, I think you understand that I'm X-ray guy, so if we will be talking about, for example, computed tomography, you will receive lots of information, you will receive 3D information, but you need really big piece of equipment to work with. So, and the equipment has to be really precise. So the challenge is to, let's say, work on equipment and do the equipment a bit smaller, user-friendly, and yeah, that will be quite a challenge.
Okay, thank you.
Okay, so I will talk about UT. There will be always conventional UT because I think NDT personnel should know basics, like physical principles. And we have also TFM, FMC, we have phase array, but I think crucial thing is always NDT personnel, qualified NDT personnel. So there will be always conventional UT, but At nuclear power plants, they're transforming now conventional UT to phase array techniques, and it's because the phase array technique can see, I will say, more in the world, and you can have more information about world, but you need also qualified NDT personnel to evaluate this data.
Thank you.
I go back in time. What we can say about NDT, all methods are old, is standard, is used historically. New methods were not revealed, and only new techniques. And these techniques bring us a lot of data, but required very experienced personnel. Because you have a lot of data, and if we don't know what we see, what we should evaluate, it's okay. I have a data, but I have no result, and or I evaluated wrong. And I think that this is a challenge for this qualification of personnel. I work for more than 23 years for producer, manufacturer of generators, and new techniques were not used. And currently, if I can say, is the same, because it's very expensive equipment, very expensive probes, calibration gauges, and so on. It's, I think that is in our branch, nuclear aerospace, where the critical components is place for using this, and bring us change to detect small flaws and exact determine their sizing.
Okay, thank you. Very nice point of view. Thank you.
Yeah, I think that, as I told you before, UT is my favorite and beneficial method. It is a very good method to find defect without destroy something, and it is much expensive yet. So many benefit. However, the NDE examiner need many training and experience to miss the finding defect and miss evaluation of the UT signal. For example, there is many limitations. What I mean is there are counterbore and root. So if he does not have much experience and good training, he is to get the root as a signal or from the counterbore signal. So UT examiner need many experience and training. In Korea, as Daniel presented us, phased UT is very popular among the industry. The RT used to be a very good technique, method. It is very easy to keep the document. But however, nowadays, the radiation exposure is a big problem. So RT is replacing to phase-3 UT. So there are many the benefit. However, also RT is the facing challenges of the radiation exposure. Okay, Teddy.
Okay, thank you. We had many interesting points of view. So sometimes, from my point of view, it's very important to find the ratio between the gain and the, we could say, price for the using of this method. Not only get the nicest pictures or something like that, but not using hammer for the fly, we could say, like in Czech language. So the second question is the use of simulations in NDT, in which areas and for which methods does it make sense? Please, Bohuslav.
Yeah, okay. The simulation, of course, started to take place in the training of the personnel and qualification of the process, and I think that's the correct place where the simulation should be. So we can use the simulation during the qualification. You don't have to prepare that many mock-ups and test blocks from steel. So that's really helpful. And also the simulation during the training of NDT personnel. As been said, the NDT personnel is really important part of the process, one of the main, I think. And during the training, also, as many samples you will use, it can help to gain experience. So in these cases, the simulations are really great to use.
Okay, so to be honest, I know only the SIVA software, and I used the SIVA software for several times for simulate like UT beam in some parts, in some critical components. But you know, you need a lot of inputs if you want to simulate also material structure. So you need like size of grain, or material velocity, and it's too difficult to find this information in some tables, so you can make some measurements first, I think, sometime before first simulation. But yes, you can use the SIVA for simulate some like shape of the crack, UT beam response, and it's good to way how to see how UT works in some material.
Okay, thank you.
I'm not expert on simulation, but I have colleagues which are, and they are protecting me to try to find proper probe, to find coverage of inspection, to find good position of probe, and so on. Is a good tool for now and for future, but challenge is also a skilled person who can use tools for simulation.
Okay, thank you.
I'm also I'm not the expert in the simulation either, but as Anna told us, we use a SIVA program for the simulation of the UT signal, or how the probe, how the UT beam impact the target, or how the UT signal can help the detection of the flaw. Yeah, I agree with Anna's talking. Okay, thank you.
Okay, thank you. I will go to the next question because we have not much time. So my third question was a little bit stalled in the previous panel discussion, but maybe if someone of you would like to add something to the previous discussion, how do you see artificial intelligence and machine learning being integrated into NDE, in which areas? So I don't know if someone of you would like to add to this question or go to another one.
For me, it's a challenge to collect data from the same component, from the same material or similar dimension. That's a big challenge for companies or for preparation data for AI. At the first for machine learning, yeah, because we need to have one or similar component with different defects or defects which can be from manufacturing process and from operation, and it's a challenge for this.
Yes, but I think that it was done previous presentations that it could be used the tool for creating virtual flaws for the resource for the machine learning.
Artificial defects. Yeah.
I think in the eddy current of the stream generator tubing in the United States, they are using automatized analysis because it is very reliable and very fast than performing by manual. However, there are some limitations when we are talking about machine learning or artificial intelligence. Somebody say the AI or the machine learning cannot create anything. Just it is very good for the repeated pattern, but it cannot create anything. He can make a good song by the taking some word or some rhythm from other one, but it cannot create any picture of the Picasso or any music of the bassman. So still there are some limitation, but nowadays in Korea and the United States, not so many young people want to work for the NDE. It's very difficult and very hard working. So due to the shortage of the experts, the using AI or machine learning is kind of very good, kind of replaceable method. So I think we cannot avoid adapting AI or machine learning in NDE. That's it.
Okay, thank you for your point of view. Thank you. So I have one little bit controversial question in the middle. So will the traditional ultrasonic technique, I mean pulse echo, be obsolete in 10 years? Maybe for Bohuslav it could be RT. Will emerging technology replace traditional ultrasonic or RT techniques? So what do you think? Well,
that's I will be maybe a bit controversial in this. I think well, there will be no pulse echo in nuclear in 10 years. First of all, we have to say that we are here in nuclear sector. Nuclear sector is a bit, let's say, atypical. So I don't think so that the standard UT will be in 10 years time will be used technique. It will disappear almost completely because, as I said, it's a question of the data. You from UTPA, from phased array or another UT technique, you will receive much more data, and also you have data with you. You can download it. You can archive them. That's not really common for classic UT. So even from the point of view of the regulators and people, and also from the point of view, I don't want to say paper, but paper it is. It's better to use the phased array because you obtain more data, you can easily archive the data, and it's starting to be also quite easy to, let's say, perform as a technician the phased array. So I'm not saying that it's that easy as a classic UT, but starting to be also quite easy to know how to perform it. So I don't think so that there will be place for classic UT in the future.
Okay, thank you.
Okay, so if we are talking about nuclear power plants, there should be phased array technique in the future, but if we are talking about general industry, pulse echo can be more cheaper, fast, and some industry, they don't need archive, like phased array data, so they need only some quick NDT inspection on some well, and for the purpose, it can be really useful conventional ultrasonic testing or pulse echo. So I don't think it's disappear in 10 years.
Okay, thank you.
Generally, I think that companies, industry companies, except aerospace and nuclear branch, will in future use both techniques, pulse echo and phased array. And the reason is cost of equipment and qualification of person, and for simply testing of simple geometry, you don't need using of phased array. You can use pulse echo. I think that not disappeared from industry. And emerging technologies replace. I think that this is running and will continue because it's the future, and as said Bohuslav, we need more data, and we need to use historical data, compare with actual and trend, using for trending and finding when our safety, control safety of components.
Yeah. Okay, thank you.
Okay, as I told you before, in Korea and the United States, phased array UT is a trend. It is very easy to keep the document and very easy to analyze, just showing the A scan, B scan, C scan, and S scan is very easy to analyze data. However, when I teach my young men, you have to learn and have to keep traditional UT. Pulse echo, it's basic. If you do not understand what is the traditional UT, then it is a kind of the house built on the sand. So even though emerging techniques is developing, however, the traditional UT is basic and is very important to let the UT technique stand alone. Thank you.
Okay, thank you. It was a very important point of view. Thank you. So, next question is, what are the biggest challenges from your point of view in NDT today?
I don't think so to find people I don't think so that it's a problem. What's starting to be challenged, it's physically inaccessible spaces or hidden spaces. So things we cannot access physically, that will be challenged in the future, because the requirements for testing going up and up. And from my experience, you know, as we prolong the lifetime of operation, for example, of the Dukovany, we discovered that we have to test and inspect more and more things. And before, I don't know, for example, before 20 years, we put something to the concrete. We won't be touching it in 30 years. But right now we want to do 60 plus. So we have to address it. We have to find a way how to test also physically hidden or physically inaccessible or a hidden object in an NPP. That will be really important topic in the future.
Okay, thank you.
Okay, so in my point of view, it's NDT personnel, because I will say qualified and experienced NDT personnel, especially in UT, on RT, and in educator testing. So I saw many UT level 2 which are asking for help of level 3, and they were afraid to take responsibility for their decision. So I think most challenge is in NDT personnel now, qualified NDT personnel.
Yeah, it's true. Thank you.
I agree with Bohuslav and Daniel, and I think that also brings challenge cybersecurity of measured data and evaluation by IAE. And AI also generate new data, and it brings requirement on the data storage, because it's big, it's a huge volume, and it's also a challenge.
Yeah, okay.
Yeah, the biggest challenge in the ND is, as I told you before, it's the kind of the personnel shortage, expert shortage. As you understand, ND is very difficult and hardworking. So many young generation do not want to learn NDE. So I think to solve the problem, we are trying to extend kind of the remote controlled the examination. For example, when we formed the retrofresh vessel examination, we have to install the equipment in the vessel manually. However, after installing examination tool, we can acquire data and analyze data in the trailer outside of the retrofit, outside of the containment building. So it will let my young generation and people, expert to feel a little bit easier working situation. It will be also very important. So to solve or to come down the challenge of the personnel shortage, to develop many mechanized or automatic technique, and let the NDE personnel working in the remotely in the Australia. Okay, that's it.
Okay, thank you. So we agree with each other that the biggest challenges will be the human source, skilled people. Yeah. My last question is, where do you see the next development in NDE? But I would like to ask you Short answer because it's time for lunch. So, Bohuslav.
Yeah, as I said before, the hidden objects. That's development we should a bit focus now, and also data management and data evaluation are really important.
Thank you.
We forgot about the drones, for example, because there are so many drones up there, and they are looking for they are doing visual testing. So I think next development will be also in the drones.
Okay, thank you.
It was the first part of our conference. I think that next development is using of manipulators and some new challenges for testing of inaccessible places.
Okay, thank you.
Yeah, I think I want to talk about the not NDT method. Nowadays, small modular reactor (SMR) will be a kind of the next generation of the nuclear power plant in the world, same as in Korea. So however, I think there is. I'm also kind of the ND expert in Korea, but nobody in Korea, no expert of the ND for the SMR. Nobody knows how to inspect, and I think unfortunately, the people who developing the SMR, they do not think of how to perform the PSI and ISI. They are just developing their technique, but they have to think of the future PSI and ISI. So the SML is to be a next generation of the nuclear power. We have to develop the NDE technique to inspect SMR. It's my opinion. Thank you.
Thank you very much. So that was all of my questions. So I would like to thank again to the panelists, Bohuslav Kolář, Daniel Dopěra, Jana Vesela, and Mr. Eus Sando. Thank you very much, and thank you too.
I would like to thank Mr. Marek for his excellent chairing of this panel session, and also to all panelists and other speakers in this session. I would like to point out that you should be back here at 2 p.m. for the next session, but now there is a lunch period, so you can go to the hall. But in any case, for panelists and speakers, I have here some gifts, so don't run fast from here. Thank you.
Okay, let me open the last presentation section before the technical tour. The last section will be chaired by Marek Miklos, and he will give you also the first presentation. He will introduce you our research infrastructure. Marek Miklos completed his PhD study in 2008 in nuclear fuel degradation at STU Bratislava. He has worked at UJV as a research scientist focusing on fuel behavior inspection and post-irradiation analysis. Currently, he serves as business development manager, linking customer needs with CVR's research infrastructure and participating in several international experts boards. Marek, the floor is yours.
Thank you very much. So good afternoon, ladies and gentlemen. I hope you had a very nice lunch, and I hope that my presentation will not put you in the sleep after the lunch. I will take this as an opportunity to present you shortly and briefly our large research infrastructure, CISR. But before I start to present, basically, what does it mean, large research infrastructure? It's basically a unique research facility which is necessary for comprehensive research and development activity with a high financial and technological demands, and which is improved by the current government and established by one research organization which can use this research infrastructure, as well the other research organization may use this infrastructure. So this is LRE, or Large Research Infrastructure. There are several infrastructures here in Czech Republic, and they are listed on the website as a map of the large research infrastructure at the website of the Ministry of Education, Youth and Sport, which you can check it here. The CVR, our company, basically historically we had 3 infrastructures which were listed on this map, and it was a research reactor, both reactors here, Řeš, then Czech part of the Gilles Horowitz reactor in France, and additional Susan laboratories. Currently, all of them are merged into one, which is named CISR. CISR means Czech International Center of Research Reactors, and again, it is basically a fusion of both research reactors, LVR15, LR0, then Czech part of the Gilles Horowitz reactors, and additional laboratories which came out in 2070s from the Susan project Susan. All of this is written and specified in more detail in our websites, or in the websites of the infrastructure itself. Here there is a short list of what does it mean or which type of technologies we have in CISR. One part is so-called CVR-based infrastructure, so that's the infrastructure which is placed here in Czech Republic, both reactors and supporting laboratories, and then the Gilles Horowitz-based infrastructure, which is the Czech 3% of access right to Gilles Horowitz. I will mention Gilles Horowitz later on, but currently it's a, let's say, biggest research reactor which is under construction here in Europe, in south of France, in Cadarache, by CA. How to access this infrastructure? So basically, we can use it, or we are using it via open access. Detailed rules can be, you can read on the web page. There are some general conditions, but also there is a huge button on the right corner where you can click on it and download the very simple application. You can fill it, send it, and that's it. It's so easy. Also, you can find on the web page in more detail the list of the infrastructures, which I will introduce to you shortly. Basically, this infrastructure can use via open access all interested parties who are meeting the definition of a user, I will tell you later on, and who are able to basically demonstrate the scientific excellence, originality, quality, and technical and ethical feasibility of the application. So basically, we are trying to use this infrastructure as effective as possible to support, let's say, excellent research studies. And that means that your application is evaluated by different type of experts, so-called CVR scientific board. And after its acceptance, then there is still one part that is a contract between the user and the operator. And then basically the open access may start. So who are the users of the research infrastructure? Of course, it's CVR, but mainly it can be individuals, it can be teams, or different type of institutions from academic sphere, business sphere, but also from the industrial sphere or public services. It can be used by the researchers, doctoral students, technical workers, because sometimes there is a need to develop something and to test their, I don't know, for example, some instrumentation which needs to be tested under the harsh environment of LVR15 reactors, or it can be used by the students who are working on their bachelor, master or PhD studies at the universities. Now I will briefly introduce you each part of the infrastructure which is listed on the webpage of CISR. First one, or I can say the heart of the CISR infrastructure is the LVR15 multi-purpose reactor, which is a 10 megawatts pool type reactor. The main use of this reactor is for material research, so irradiation of different type of materials, from steels, through claddings, through concrete, etc. We don't do the irradiation of the fuels, nuclear fuels. For this irradiation, we are using different type of irradiation rigs, capsules. In past, we had a very nice experience with operation of in-pile water loops for in-pile corrosion studies, but this was ended a couple of years ago. And we have several out-of-pile loops, as I will introduce you next slide. Also, the reactor is currently used for isotope production. We produced isotopes for medical purposes as well as industrial purposes. For example, LVR15 is one of the main producer of Moly-99 for all around the world, but also we worked with different type of customers and universities on isotope production like terbium-169 or lutetium-177, 77, sorry. Also, we work with the semiconductor industry by irradiation of silicon crystal ingots using our NTD or neutron transmutation doping. And around the reactor, there are several, concretely 9 horizontal channels where we have 9 nice neutron beams for basic irradiation studies. The second reactor, LR0, is a light water zero power reactor with versatile core arrangement. This reactor is mainly used for code verification, or critical experiment, different type of benchmarks inside the neutronic valley, I can say. I mentioned the experimental loops. A lot of people in my career, they are asking me, what does it mean loop? Does it mean that you can move some environment inside? Basically, it's a device which is where we are able to simulate the real conditions which are happening at the power plant. So we can reach the same temperatures, pressures, but also by putting the in-pile part of the loop into the LVR15 core, we can simulate the neutronic environment as well. Currently, we don't have any in-pile loop in operation. We have only out-of-pile loops in operations. Which of them? They are listed here. So there are 2 high-temperature helium loops. One is called HTL1, the second is placed in Pilsen as Allegro. These loops are working under high temperature, up to almost 900 degrees, as a coolant is used helium. Then we have a supercritical carbon dioxide loop, several metal liquid loops, Flyby loop working with molten salt based of barium fluorides, and then supercritical water loop and ultracritical water loops. I'm really sorry that I'm not going into very details of these each loop, because that can take a lot of times, but you can read a lot of information at the web pages. When you do the irradiation of your material, you also want to study the material, how it behaves, how the neutrons affect its mechanical properties, and for this we are using our hot cells laboratories, which are basically equipped by different machines and devices where we can, after the irradiation, prepare the specimen. We can do several mechanical testing, like grid test, tensile test, different type of tests, and also some basic microstructural studies using our SEM or nanoindenture inside the semi-hot cell. Here we are working with variable types of materials. We use primarily, we are working with stainless steels or different types of steels, also with zirconium niobium alloys, which are used for cladding materials. Currently we are starting with silicon carbides, which are potential material for cladding materials for future reactors, but also we work quite a lot with concrete and aggregates. After the, let's say, big mechanical testing, it's always good to understand how the microstructure behaves. For this, we have microstructural and microchemical laboratories, which are equipped with different microscopes. Here, I would like to say that I'm happy that these laboratories are placed in a control area, so we can use them also for study of irradiated materials. For the basically studies of how the radiation is transporting via different materials, we are using our HPG spectrometry laboratory, where we are using different benchmark assemblies composed by pure materials. These are basically spheres with different diameter. And we have several neutron sources. Mainly we are using the californium and americium beryllium neutron source. And also this laboratory is equipped by different spectrometry equipment. Also, as we have seen in previous section, there were a lot of very nice presentation regarding non-destructive testing, regarding long-term operation of nuclear power plants. But very important part of the living process of the power plants is the qualification of the materials and equipment which wants to be implemented at the power plant. For this, we are using so-called qualification laboratories, which is combination of three main laboratories. The first one is a local laboratory, where we can simulate so-called loss of coolant accident and test different type of cables, instrumentation, but also like motors, valves, and check them if they will survive such kind of conditions. The second laboratory is high voltage testing laboratory, mainly using for isolation, testing of the insulation and cables. And the last is so-called gamma irradiation laboratory, where we are using cobalt source and we are using a specific device to heat up the specimen or cool the specimen under this environment and do the irradiation in front of the cobalt source. And of course, to support a wide range of chemical analysis for research and development applications, we are using the chemical laboratories, which is also equipped with different types of spectrometers, microscopes, etc. My last slide, and also very important slide, is the Jules Horowitz reactor. I can spend hours to introduce this reactor, but very shortly say this reactor is currently the most powerful nuclear reactor, which should be used in the future for material and fuel irradiation studies with the capacity of 100 megawatts. This reactor is currently under construction in south of France, in Cadarache. Reactor is already placed in the S3 roadmap, as well as in the Czech travel map, which is covering the large infrastructures for this type of research. There are many organizations, starting in France, Belgium, Finland, Spain, Sweden, but also Czech Republic, who are creating so-called international consortium who is building this reactor, and UJV together with CVR, we are responsible to build the important part of the reactor, and that's hot cells, where you will do all the basically unloading of the irradiation rigs or capsules, etc. And by this work, basically Czech Republic in future will have up to 3% of access right to this reactor. And very important information, because this reactor originally should be in operation in 2014, I think, but there were a lot of delays. Now, the last information for last 2 years, which I'm very happy because I'm involved there, is that the first criticality should be expected in 2032, which means 1 year of 1 year of testing of the reactor, second year of testing of experimental devices. So let's say the first experiments may start in 2034-35. And that's all for my side. So if you have any questions, you can do it now or later on. Thank you very much. And because I have the microphone, I will ask if there are any questions. If not, then I will ask the first presenter. Let me see. And okay, and that is Mrs. Denisa Janova. And let me see the first presentation. Ms. Janova is a student of Material and Technology at the University of West Bohemia in Pilsen. She's in the last year of her master's degree, so congratulations and cross fingers. And she has been working partially for the last 2 years at the metallographic laboratory. So the floor is yours.
So thank you. Do you hear me? Good. Oh. Okay, so good afternoon. My name is Denisa Janova, and I'd like to talk about my former bachelor thesis. And this thesis was on the porosity analysis of 3D printed products. And my leaders were Mr. Beneš and Mr. Bricin. And also this bachelor thesis was created in cooperation with Open Access Project. So from this point in, I was able to use laboratories and equipment. Firstly, I'd like to introduce additive manufacturing. So despite the fact that additive manufacturing is a new technology, it's going through progressive increase, and products of additive manufacturing we can find across many sectors of industry, for example in aeronautics or even in medicine. But products of additive manufacturing have relatively huge values of porosity, and porosity has a huge impact on mechanical properties. So determination and monitoring of porosity is a very important issue. Firstly, I'd like to show you the structure of my presentation. In the first part of my presentation, I'd like to introduce additive manufacturing and concretely method DED. Then I'd like to introduce porosity, and I will talk about types of pores. And in the next part of my presentation, I will show you some results of my experimental part. In the next part of my presentation, there will be conclusion, and also in the last or final part of my presentation, there will be space for questions. So firstly, I'd like to talk about additive manufacturing, and concretely about one method, which is method direct energy deposition. I will talk only about this method because in my bachelor thesis there I was focused on samples which were made by this method. So what is DED? DED is a method which use focused energy source for melting and fusing material. Material can be in form of wire or in form of powder, and products are deposited layer by layer. And also this method can be used for making a new part from a sketch or to adding material to existing ones. Now I'd like to briefly talk about porosity. So porosity is considered as a defect, and also porosity, as I have already mentioned, porosity has a large impact on mechanical properties of the products, and current material science divides porosity into 3 basic groups and divides this porosity which are produced during additive manufacturing process. First type of pores are keyhole pores. The second types of pores are lack of fusion pores, and the last group are gas pores. Keyhole pores are caused by exceeding energy input during process, and these pores are called because of their shape. The second group are lack of fusion pores. These pores are caused by a low value during process, and during the process each particles of material are not properly connected, and they create a lack of fusion pore. And the last group are gas pores. These pores are caused by gas contamination of material, and these pores are relatively tiny, and also these pores have relatively spherical shape. So for monitoring porosity, it's very important to define and find concrete type of pore, distribution of the pores, and also frequency of the pores. Now I'd like to show you methods what we used. So we used non-destructive methods and also destructive method, which was light optical microscopy. Now I'd like to introduce samples. So in cooperation with Development Institute Contest in Dobřany, were made 3 samples. These samples were made by method DED with tactics zigzag, and the list of some process parameters is over here. And also for manufacturing of these samples were used same process parameters. And now I'd like to start with non-destructive methods and their results. Firstly, I'd like to start with X-ray testing. This method is based on radiation of energy through the space, and also this method uses one part of electromagnetic waving. This method hangs on quality of the surface, and also this method has some distinguishability, which is about 250 micrometers. And as you can see on these pictures, this method did not observe any presence of any pores. And also in that case, that samples have defects, but these defects are under some distinguishability. This method should not observe any presence of the pores. And now I'd like to show some results of ultrasound testing. So this method is commonly used in material science. And in this case, there were used 2 methods, pulse echo and phase array. And also, these examinations were made in 2 directions. And for examination were used 4 types of probes. And as you can see in this table, any examination did not observe any presence of any defect. Here you can see a sector scan of a sample A, and linear scan, and also a scan of a sample A in direction of the layers deposition. And also with this method, alternation for individual probes were also monitored. And here you can see each attenuation for each samples in each direction and for all probes. And now I will talk about helium pycnometry. Helium pycnometry is also a non-destructive method of testing. And from the first step of this experiment is necessary to find out the wave of the sample. In the second step of this experiment is a sample put into a container, and also in this container are streamed molecules of helium. And then when pressure in a container hits some specific value of pressure, the machine will automatically repeat a value of density. And as you can see on this slide, the highest value of density had a sample C. And now I'd like to talk about destructive methods and their results. As I already mentioned we used only light optical microscopy, and microscopy is considered as a destructive method because for observation is necessary to some special preparation of the surface of the sample, and commonly are samples sold into some tiny parts, and these tiny parts of these are observing. And in our case, all 3 samples were sold into next to tiny samples, and these plates were observing. And as you can see, there were observed only gas pores, and these pores have sizes in range from 1 to 10 micrometers. And also on these samples there were observed relatively low values of porosity. So in conclusion, any non-destructive testing did not observe any presence of the pores, but only microscopy did observe pores. And microscopy also told us about types of pores, distribution, and frequency, and also but microscopy isn't the best choice to detection, because with microscopy we can only see a tiny plate from all volume of the sample, and better choice is to combine destructive and non-destructive methods of testing. And also I'd like to mention that microscopy did observe pores with sizes in range from 1 to 10 micrometers, and it means that these values are lower than distinguishability of X-ray testing or of ultrasound testing. And also all samples have had relatively low values of porosity. And I'd like to mention that on this topic continued my leaders, Mr. Beneš and Mr. Bricin, and they created some papers. And this is the end of my presentation. Thank you for your attention, and now it's time for your questions.
Okay, thank you very much for your presentation. Are there any questions? Oh, good. Perfect. Wait a second.
Thank you for the presentation. These samples are for the same project on that I participated, and from side of NDT, and your results correct with NDT, because so small defects, porosity, which is the main defects of printed parts, is under detectability limit of both volume methods, that is RT and UT. If we will be able to see, these poros should be higher than approx 150 or 2000 microns, and then should be see on UT. I'm focused on UT, and or if frequency would be so high and less clusters of porosity, and then we will be able maybe to see them. Thanks.
Perfect. Thank you very much.
Thank you for this interested comment. Actually, that was my question, so you just responded. I would like to also ask if you, if the material which was produced by Comtesse company, it was just done by additive manufacturing, or if there were any application of high isostatic pressure or something, this type of methodology?
No, my bachelor thesis was only focused on samples which were not after post-processing treatment, but also there was some possibility to continue my bachelor thesis, because one of the samples were sent to Sweden, and there passed through HIP, but I didn't have enough time to write into my bachelor thesis because deadline. And so I think that on sample what go through the HIP continued Mr. Britzin, and they created paper.
Okay, thank you very much. So if there are no questions. If there are no other questions, I would like to call second presenter, Jaroslav. So Jaroslav Šoltes earned his master's degree and PhD in nuclear engineering in Czech Technical University in Prague, specializing on research reactor utilization. Within 14 years of experiences at CVR, he progressed from junior researcher to department head, working on isotope production, material irradiation, and neutron radiography. He has led international projects, supervised students' thesis, and is the author of numerous peer-reviewed papers and several patents. And he will give you a very nice presentation about our calorimetric measurement, which is one of my favorite projects here on CSER. So the floor is yours.
Oh, thank you, Marek, for the introduction. I will give a talk on the calorimetric measurements on the heart of the CSER infrastructure, the LVR-15 reactor, which was introduced by Marek in his talk. And basically, during today's presentation, I will introduce a project which started only a few months ago, and the main part of the project is going to happen towards the end of the following year and in the first half of 2027. So the half of my presentation will be dedicated to the background, why these kinds of measurements are important in reactor physics. And towards the end of the presentation, I will come to the current project status, to the outline for the next months. I will talk a little bit what results we expect to receive from the project, and by the end, some conclusions should come. Here on this slide, what you see is the core of the LVR-15 reactor in the shutdown state, and the nice Cherenkov radiation surrounding the fuel installed in the core. When it comes to calorimetric measurements in terms of reactor physics, these measurements are aimed to the determination of the nuclear or radiation heating that occurs in the active core during the reactor operation. And to know this value is very important in terms of material irradiation experiments that occur at the LVR-15 research reactor. I'm not going through the utilization as this was already mentioned in Marek's presentation, but for the material research experiments, there are two key features. One is the received neutron fluence and radiation damage which the material receives. And the other important parameter is the irradiation temperature which the material is exposed during the irradiation. In most of the irradiation experiments, we aim to have this temperature as close as possible to the temperature in the environment of the nuclear facility, for which we aim to use the material that we irradiate. And as the phenomenon of nuclear heating occurs in the reactor, most of the samples heat up during irradiation, and we need to be aware of the temperature that the samples will have through the irradiation, as this is really a key factor when the material is evaluated afterwards. We have several techniques developed to calculate this nuclear heating. However, the calculation is one side of the problem, but when it comes to the practical results and the practical data from the reactor operation, we are still finding some gaps between the calculation and the measured data, and there are still some approximation used in our models, and the methods that we use needs to be really qualified on precise measured data. Here on this slide, you can see the active core of the LVR-15 reactor. The violet elements are the fuel elements surrounded by the beryllium reflector blocks. We can assemble this core in a very flexible way, and in this way it is capable to house multiple material irradiation experiments, also radioisotope irradiation for industry and medical purposes, and also providing neutrons for neutron research on the neutron beamlines surrounding the reactor. We have listed here the neutron flux values which are received in the core. These values were tested and can be predicted by our calculation programs in a very good way, and these values are validated through multiple experiments that have been conducted on the reactor in the past. However, as precise as we are for the neutrons fluence and neutron flux value predictions, we want to be also for the nuclear, mostly gamma heating values. And for this reason, we designed an experimental program comprising gamma calorimeters with a movable system that should be capable to give us these radiation heating values to prove that our computational codes give the right results, and to be capable of modeling for the design of future experimental designs for material testing. One of our key material testing experiments is the so-called OCA brick. It's a rig that was designed 6 years ago, and it's a rig aimed to receive high neutron radiation damage, which we can achieve that we place it into the central cavity of 6 tube fuel elements. A fuel element is showed here on this slide. It's an 8-tube standard type element. If you remove these 2 central tubes, you have a 6-tube fuel element in which you can place a material irradiation rig of so-called OCAP type. In this rig, we irradiate fuel cladding in 4 axial levels. However, the nature of the experiment allowed us to monitor only the temperature in the uppermost level of the experiments, where 4 samples were located, all 4 equipped with thermocouples, giving us online information about the temperature during irradiation. For the other levels of the rig and the samples, we only rely on our computational models, which we need to qualify in the most possible way, because as I will show you some results that we have with this experimental device and the other ones, that are some uncertainties that our models do not cover. Here is the temperature measurement data that was achieved from the first generation of the OCA brick. The rig was designed using our calculation models, which is a combination of neutron transport code, MCMP, and thermohydraulic code afterwards, which uses the inputs from the MCMP neutronics code. And the device was designed to have equally same temperature in all 4 samples located on the uppermost level. However, as you see from the measured data, there is a deviance of 20 degrees C between the individual samples. And this information led us to more investigate the situation on the radiation heating calculation and its distribution along the irradiation device. A similar experience we had also on other irradiation devices, like here the rig for liquid lead lithium environment. For this rig, we aimed to have 450 degrees C maximum during the irradiation. And from the nuclear heating values that we calculated, we should have received this temperature by having a gas mixture of 50% nitrogen and 50% helium in the irradiation device, which gives us some insulation properties to receive the proper temperature. However, when we put this device into operation, we noticed that 90% of nitrogen were exactly required to reach the required irradiation temperature. And for this reason, the values that were predicted by our codes were too high, and the same phenomenon was observed in a rig for irradiation of copper, chromium, zinc alloys intended for fusion purposes. Here we have aimed to have like 4 vertical sections, each with different temperatures. However, during the irradiation, where the device was designed upon our calculations, we received only 2 temperature ranges as listed below. So all of these data that we gathered together gave us the information that the nuclear heating that we calculate is overestimated. And we also produced a test OCA brick for a calibration test. This OCA brick was capable to measure the radiation heating in all 4 levels because it was not occupied by full-scale samples. And what we have seen from the outcomes in all cases that were measured, the upper 2 levels were in alignment with our calculation prediction when we subtract the overestimation. However, the bottom 2 levels gave much higher values than the calculation predicted. We also performed a cross-comparison calculation exercise involving UJV, VTT, and CEA in 3 different calculations code to have an idea which part of the nuclear heating is overestimated in our codes. It was the case of delayed gammas. We were able to find the source of the overestimation and fix this problem for the future calculations. However, still the answer for the axial distribution of the nuclear heating did not come from this simulation exercise which was conducted. So for this reason, for the calorimetric measurement, we don't want to perform only static irradiations, but we want to design the system in a movable way so that we can perform axial shifts of the calorimeter during reactor operations, and we can measure the vertical profile of the nuclear heating in the reactor, especially for those reactor positions in which we are installing the irradiation equipment. We cooperate on this project with CEA, who are the designers of the calorimeter, which they originally designed for their reactor Osiris. And they adapt the reactor so that we can house it in our LVR-15 research reactor. And our part, the contribution of the CVR, is the design of the movable system which could shift vertically the calorimeter during the reactor operation, and the whole profile could be measured in this way. What we expect to receive as outcomes is reliable data and verified models, which will be used for the future generation of the irradiation experimental devices. We will produce 2 systems of this kind. One that can house a ionization chamber just to measure the gamma flux, and the other one to house the CEA calorimeter, which will perform the radiation heating measurements. At the current stage, we performed first demonstration unit of the movable system, which we currently test. And during the second half of the following year, we should integrate the CA calorimeter into our movable system, and the measurements should happen in the first half of 27. We intend to present these, the outcomes on the research reactor conferences and within the FIDIS2 community. The calorimeter, it's based on two cells, where one is the sample cell, where the radiation heating occurs. Then we shift with the movable system the calorimeter a few centimeters upwards, and to get the reference cell in the same position as the sample cell was a few moments ago. The reference cell is equipped with heaters, and with the heaters we receive the same temperature in the reference cell as was received in the sample cell. And upon the heater's output, we can distinguish the nuclear heating of the values from 0 to 3 watts per gram, which should be pretty well enough to cover the whole range along the axial height in the LVR-15 reactor. And this slide is dedicated to the movable system, so you can see a system of a chain and wheel, which will be attached to a step motor, and this system is currently in the development phase. The first demonstrator was built, and the key feature is that from the calorimeter there will be 8 cables reaching out to the upper part of the reactors and to the reactor hall, and we need to guide these cables to a trenching system which is equipped to the movable system. And this is the challenge that we are currently facing with and preparing, and hopefully as a Christmas gift we can overcome the first issues that we encountered, so that we can make out-of-pile tests of the device in the first half of next year and prepare the whole system for calorimetric measurements of LVR-15 in 2027. So I've came to the end of the presentation. So if you have some questions, I'm open to answer. Thank you.
Thank you, Jaroslav. Are there any questions or comments from the audience? Good.
I would like to ask you if there is a plan to operate the calorimeter through all the experimental campaign, as many things can change during the full campaign, like a position of the rods and so on.
Yes, thank you for the question. I didn't mention it in the presentation, but our reactor campaigns take approximately 4 weeks, and the core develops through the run of the campaign. And the device is intended to be capable to measure the profiles through the whole campaign, so we will have an information how the nuclear heating develops and how each phenomenon that occur, like the compensation rod movement and the fuel burn-up, affect the developed heat in the reactor.
Maybe one comment. I said that this is my favorite project on the CISR. Basically, here, as you can see in the presentation, the project is not only about to measure something. Of course, that's the most important. But from my perspective, the most important is that we are basically a testing of instrumentation from CEA, because they were working on calorimeter and ionization chamber and using them in 2015 at the Osiris reactor. But since then, when they closed the reactor, they had no opportunity and no chance to test their devices. So now basically this is the project where they can test their devices using our reactor via open access and at the CSER. So thank you, Jaroslav.
Thank you.
And the next presenter is Fiona Harden. Fiona graduated with a mathematics physics degree in 2010 and completed her doctorate in physics in 2014 from the University of Aberdeen in Scotland. She has worked in several research institutes, including BAE Systems in UK, CERN in Switzerland, ICIS Neutron and Muon Source in Oxfordshire, and now she's working for UK Atomic Energy Authority, where she's focusing on fusion-related research. Her current focus is on the development of the test rig for providing fusion-related principles. And for me, personally, she's the most passionate scientist and manager in one person. So Fiona, the floor is yours.
Words are very kind, Marek. Can everyone hear me? I'm quite short, so I'm aware that I'm looking over the screen. So today I'm here representing the UK Atomic Energy Authority, and hopefully I'll give you a bit of an idea on what we are doing, but also why I'm here and why we are collaborating quite closely with CDR. The particular project I'm working on is called HICUS, and hopefully you'll get a better idea of what we do and what we're planning to do over the next few years. So the first thing I do want to mention here is the two missions that we have at UKAEA and UKIFS, which is STEP. So realistically, we want to lead the delivery of sustainable fusion energy and maximise the scientific and economic benefit. And the thing with STEP, which is a separate programme, is to deliver a UK prototype fusion energy plant, hopefully delivering energy to the grid and proving that concept. The idea at the moment is to be delivering in the 2040s, and so we're quite a fast-moving project. Firstly, for those of you who aren't really familiar with the fusion sector, just to give you a bit of an idea on what has happened over the years, the JET programme, so this was basically a physics experimental programme to find out if the concept of fusion could happen. This is where we had creation of the plasma. It's a world record-breaking facility as well. That is now in decommissioning. The experiment was very successful. We then moved on to another experiment, the MASS-U. So this is basically a project that is developing a spherical tokamak. So tokamaks are normally of a torus shape. The MASS-U project is trying to understand whether this can be achieved, looking at the concept of it and seeing if we can develop that and learn lessons for that for STEP. We're then moving on to STEP, which is the main programme the UKAEA and UKIFS are now working on. And the idea here is that we want to create a working prototype so that we can deliver net energy to the grid. What you have here at the bottom corner is the site that has been chosen for that. So this is actually a large, it's substantial. You can see the buildings there, and this is the place that has been chosen. If STEP works, we will have proven the fact that commercial fusion is viable. So this is then hopefully moving towards the future of making fusion energy successful. So what am I here today to talk about, and why do we need to be working with facilities like CDR to do irradiation testing? One of the critical things within any tokamak are the magnets that are developed. Within STEP, we have selected high-temperature superconducting magnets, and these are REBCO samples. So the picture here is of the REBCO sample. You see the REBCO is actually very, very small. The purpose for this is that we want to be able to use REBCO, and this is high-temperature superconductors, which operate at around the 20 Kelvin mark. Of course, using high temperatures means that we have to put less energy in order to cool that down, and the functioning of it will hopefully be more energy conservative. But one of the critical things within any development of this tokamak is the fact that the magnets make about 25 to 30% of the total cost of the tokamak itself. STEP will be working continuously, and so we need to understand how long these magnets can work and at what point do we need to be replacing these during any kind of operation in any run. And this is why we need to do things at operating conditions. So when I speak about fusion-like operating conditions, the magnets need to be at temperature, so at 20 Kelvin. They need to be under high-energy neutrons. There needs to be gamma irradiation. It needs to be carrying a rated current, as that's what makes the superconductor work. And it also needs to have fields and strain applied to it. Here's some information. If you want to scan the QR code, feel free. This links to a lot of publications linked with the STEP program itself and speaks a lot about the design and things there. The key thing here I want to mention is the fact that we are putting a magnetic field of 3.2 Tesla through it, and we're looking around sort of a DT fusion power of 1.68 gigawatts there. So do have a look at this if you have an opportunity. But when it comes to the analysis of the REBCO samples, the critical thing is, as I say, that we need to understand how long these will last for. This number here, let me get the mouse, this number here, there we go, the one in red, is the total neutron fluence that we anticipate the REBCO samples are going to live for before they show areas of damage. And when I speak about areas of damage, I'm speaking about the way in which that material behaves. So the current carrying capacity of that material will decline. There is evidence to suggest that under neutron irradiation, that current carrying capacity improves, and there is a certain point in which it then starts to deteriorate. And that's what we want to understand with this. Realistically, the estimates, the theoretical calculations, is it will last 430 days. But this is all theory, and we haven't actually had the opportunity to irradiate under high energy neutrons. We've done this with ions, we've done this at gammas, we've done it maybe a little bit at temperature, but we haven't yet done this with high energy neutrons. And that's why I'm here today to speak about our relationship with CVR. So the critical thing here is that a fusion plant does not exist. And therefore, because a fusion plant doesn't exist, we have to go to as close as feasibly possible to the energy spectra that we will get from a fusion plant. And lo and behold, the fission plant, we are relatively happy with what we are getting. But the critical thing I want to highlight here is the high energy region. And this is the point, anything above 0.1 MeV. That's what we are really interested in at the moment, because that's the high energy neutrons, and we want to be trying to get the neutron fluences under those high energies there. What we then did is we thought, right, okay, we need to look around and see what facilities are out there and what we can potentially do. We did a feasibility study, and the outcome of that was that CVR was the perfect facility to do such an experiment. Now, why, you might ask? The reason is that CVR is such a unique research facility because it provides us with horizontal channels going into the core of that reactor. So what this means is that you can perform experiments, you can have first-of-a-kind experiments being developed at these extremely high-energy neutrons, which, to be honest, you can't really find elsewhere. Yes, you can put things into the vertical core, but this is very complex, and we want to do measurements while we are irradiating, and we also want to keep that sample cold as well. So CVR was the one that was selected, and we've been in collaboration with them since, I think, 2023-ish, I would say. Now I'm going to speak a little bit about the design, just to give you a bit of an idea on what we're doing. So, first thing, just to remember in your head, we want to test the superconducting materials. We want to test them while they are cold, so while they are at 20 Kelvin. We want to irradiate those materials. We want to keep those samples at temperature when we do the critical current measurement, so when we apply a current through it. But we also need to apply a magnetic field to that because it's a magnet, and we want to see how it affects with changes in the magnetic field. The reason I'm showing you this picture is to show you the space that we have to work with. The red arrow here is basically the HK5 channel. This is the channel that we've been allocated. It gives us the ideal spectra that we're looking for as well. But the shutter itself, the shutter into the channel here, is around 10 centimetres in diameter. So this means that we have to work around that when we're considering about how we're measuring and how we're going to be applying the field and how we're going to be doing all the bits and pieces that we need to for this experiment. Also highlighting here is the diagram of the channel itself. You'll see it's quite long. It's probably around 3.6-ish metres. The fact that we want to go into that channel, we also need to consider the fact that we don't want to cause any damage to that channel. We don't want to be interfering with that channel at all. So these are a lot of concepts. I'm just putting these in your mind at the moment, and then I move on to this part. So, as Yaroslav mentioned in the previous talk, the irradiation campaign is approximately around 4 weeks. So, during the irradiation campaign, you cannot get in to replace that sample. So, we may as well optimise what we're trying to do during the experiment. We could theoretically irradiate the entire up to the neutron fluence that we're looking for. So this is 3 times 10 to the 18. We could get that in about 2 days if we went right to the end of the reactor core. Well, the end of the channel, I should say. The thing is that we don't get access for another, 26 days. So we may as well optimise the use of this. And this is where CVR is perfect because of the fact that it has these horizontal channels here. So it's a user facility. So what we've done is we've looked at the way in which we can maximise the use of the irradiation campaign, maximise the use of the rig for the amount of data that we can get from this, and through this we've identified that between 10 and 20 centimetres from the end of the reactor channel is where we would ideally like our sample to go. Theoretically, we should get the total irradiation after about 9-ish days. But the reason I say the irradiation at 9-ish days is because I now move on to the experiment itself. 3.10 to the 18 neutrons per centimetre squared, neutron fluence in 8.7 days, technically. But we don't get in for, another 20-odd days. So we have to optimise this. The space here is what we have, so the arrow here shows you where in the CVR facility, in LVR 15, we will put our rig. And this here is an example of a top-down view of what we would be looking at. So you have the core, you have the channel, you have the bioshield, you have the shielding on the outside, and then you have the experimental here. So this part here is where we hope to put our experiment. And this here is just a CAD illustration of what we're wanting to do. The bits here that I really want to highlight to you is this here's the cryostat. The cryostat works in keeping the entire rig cold. So this is that cold, ticking that off, 20 Kelvin, great. We have our measurement system here, which is for the critical current measurement system. So this is looking at the operation of the superconducting materials. This here is where our magnet will be placed. We want to apply a magnetic field. There is no way we are putting a magnet very, very close to the reactor core. So we are basically irradiating, then measuring. But because of the ability to operate during those full 28 days, we will be getting sequential measurements during that campaign. And what do I mean by that? So we will have our sample at the end of the rig arm. So this here is the rig arm, and we have our sample, which is right at the end there. Now this sample is a very small sample. This is around, what, 5 centimetres by 2 centimetres, and we will have our Redco tape there. We will have our connectors there. This is where our sample will be, and so we need to be able to put our sample as far into the core as we require to get the irradiation that we need. The other thing here is that this entire rig arm will be cold. So this entire bit will be cold, and our sample will be kept cold through conduction. And this is where the cryostat will work, and we are currently doing some investigations about the type of materials that we'll need for the sample holder. What is operation going to look like? And again, I really need to reiterate the fact that this facility allows us so much flexibility to do this. We have our sample is within the rig arm. We then cannot enter. We turn our cryostat on, we bring our sample down to 20 Kelvin. We then move our sample to the measurement position. So we move it there, we turn the magnet on, and we ramp the magnet up 1, 2, 3, 4 Tesla. We take a critical current measurement at each of those points. Then we open the shutter, and we place our sample into the reactor. So we place it into that horizontal channel. We irradiate for a certain period of time. This is through calculations that we will collaborate with CDR on. And we will then remove that sample back out, close the shutter, turn the magnet on, critical current measurements taken, and then we will move back and forth several times during the irradiation campaign for those 28-30 days. At the end of that, we will simply move out, and then we've got to wait for cool down time, which is approximately around sort of the 6-week mark. So ideally for this, we'd be doing irradiation campaign every other campaign. But because we are still looking at the samples, we can potentially optimize the sample holder, and we just want to really understand at what point does the neutron irradiation affect the behaviour of those superconducting samples. And through these iterative measurements, we should really get a good idea about where, when it's happening, and how it's being affected during the irradiation campaign. So this, I think I've mentioned the fact that we'll have a cool down time. We will be trying to use it as much as we can, and this is why we're trying to optimise it as well. So what are we doing now? Last couple of slides. We are basically trying to work out how we are going to do it in the UK, plus building that rig over here. We're looking at different ways in which we'll install, commission, how we're going to operate this for the several years that we would be in operation. We want to build a test rig at the UK site. So we want to build that test rig, and that will allow us to have a working mock-up for when we then make another high-cris rig at the CBR facility for installation. So this means that we have a working mock-up on our site, we have an irradiated facility here, and what this means is that we will be able to get a good understanding of if there are any problems, we'll have any good maintenance, and all of these things we'll be able to understand. So this is what we're doing. Experimental rig 1 is our let's see if this works rig that we're currently in development at UK AEA. This will then lead on to a full-blown mock-up, and this will then lead on to the mock-up influencing the physical rig at CBR itself. That's pretty much me. What I do want to highlight just before I go is that this work isn't by me. This is by a tremendous team that myself and my project manager Sophia are working with. And I also want to thank the close collaboration with CVR, because we've done a lot over the past couple of years to get this to the position that it's in. So I'm happy to take any questions or happy to speak to you afterwards.
Thank you, Fiona. Thank you for a very interesting presentation. Are there any questions or comments from the audience?
I would just ask you a simple question. What do you see as a main challenge for this experiment? And maybe one step back, what do you see as the main challenge for STEP React?
How long we got? This is the thing. For this experiment, there are so many things that can go wrong, because we're applying a field, we're making it cold, we are putting a current through it, we're doing measurements, we're wanting to put in equipment so we can understand what's happening during the irradiation. Each one of them in themselves is hard, and so trying to do that all together, I think, is quite a challenge. Let's put it like that, quite a challenge. So the hope is that we will be able to just continue working with CVR, be able to do any risk analysis that we're having to do, and this is where, fingers crossed, everything's going to work under irradiation. In terms of STEP in general, we're a fast-paced program. The program itself, there are so many questions, there are so many unknowns about fusion. This is the development of the blankets, the development of the magnets, the development of the tokamak, which is going to be small because it's a spherical tokamak. There's the material choices, the breed-in, the lithium breed-in, not the lithium breed-in, the breed-in of the tritium. So we've got so many challenges. I couldn't name just a single one. It's all fun.
I can say, if you can go to slide number 11, well, the biggest challenge, or there are several challenges here, talking about the high risk. The first part is the picture at the very top is the space. Actually, there is not so much space. So that was like...
Is it this one? Yeah, less than a meter.
Yeah, for example, this one, yeah.
Less than a meter.
Like, I remember when we started to talk with Fiona and her team in 2023 or something like this. There are people from Fusion, they work on a jet where you have big spaces, everywhere space. And then they ask, okay, so how much space you have at the LVR 15? And we say, not so much, it's like a couple of meters. Oh, that's fine, you should come. And then they come and they see, oh, there is not so much space. So the space, that is a really huge challenge, but I'm very glad to, when I've seen the first designs which were presented right now. The second big challenge is the magnet. Because there are, on the previous picture you have seen that there are other experimental devices, and now all the people, especially from the Academy of Science, they start to be like, oh no, shit, there will be a magnet for Tesla. It will affect our experiment. So that will be really another challenge. And the last challenge, at least from my perspective, will be the cooling system, because that maybe it can create quite a lot of noises. And if we will place it right there at the reactor hall where you have people coming around, it will be not possible to work there in a polite way. When you put it on the roof, of course, then all the animals and all the city of Rzesz will listen it, but that will also affect the cooling system itself. So that are a lot of challenges there.
Thank you to your colleagues. Thank you to you and your colleagues for working with us and having those conversations with us. So it's massively appreciated.
So thank you very much. So if there are no other questions, I would like to ask the last presenter. Thank you, Fiona. So the last presenter is from my alma mater, which I'm very happy to host her here. It's Sofia Gašparová. She graduated in nuclear and physics engineering from the Slovak University of Technology in Bratislava 2 years ago. Her research focuses on the characterization of radiation damage in structural materials for advanced nuclear systems, especially nuclear fusion, a topic she continues to pursue during her PhD at the Institute of Nuclear and Physics Engineering. She specializes in non-destructive techniques, particularly positron annihilation spectroscopy, to investigate the microstructural changes in irradiated materials. So the floor is yours. Thank you.
Okay, so thank you for the introduction. So hello everyone. Today I'm going to tell you something about the project Komár, which for those who don't speak Slovak or in Czech, it means mosquito in English, but has nothing to do with mosquitoes. It actually is an acronym that comes from a Slovak translation of structural materials of nuclear facilities. And this whole project is basically the main topic of my dissertation thesis, which can be summarized as a study of early stages of radiation damage of some perspective materials by positron annihilation techniques. Big part of this project is neutron irradiation of the samples, which was possible thanks to the CSER infrastructure, but more on that later. So the outline of the presentation is as follows. First, I will explain more about the project and tell you something about the materials we chose to study in this project, and then I will move to the methodology that was used and share some outcomes and results from this project. So, as I said at the start, the project focuses on early stages of radiation damage. So we are talking about really small DPAs, below 1 basically. And we studied in some perspective materials that have applications in modern nuclear facilities, such as Gen 4 or fusion reactors. The materials that are being studied are some various ferritic martensitic steels and ferritic alloys, which were also supplemented by pure iron. And one part of the project is basically to compare these materials and their radiation resistance and microstructural response to the radiation. And the second part of the project is we expose these materials to 2 different environments. One is the neutron irradiation, and the second one is proton implantation. And although we have such great facilities as here in Rzeszów, where we can get our samples irradiated by neutrons, as you may know, there are some disadvantages to neutron irradiation, such as the activity of the samples or the long duration of the experiment. So the project also addresses the application of ion implantation as a surrogate for neutron-induced damage. And to actually study this material somehow, we use something we call positron annihilation spectroscopy, which is a non-destructive spectroscopic technique that helps us characterize the microstructure and helps us study vacancy type or open volume defects in the materials. Okay, so here are the materials that we chose to study. First, we have some FM steels. So there is the T91, which is a commercially used FM steel. Then we have the modern Chinese steel SIMP to have some comparison between the commercial use and some modern steel. And the last one is Eurofer strengthened by dispersion oxides. So we also have some strengthened version of that steel. Then we have some ferritic alloys. The first one is ferritic alloy with 22% of chromium, which has some possible applications in Gen 4 reactors as fuel cladding because of the high amount of chromium. It has also 5% of alumina, which also promotes the resistance to corrosion. And we complemented this alloy with pure iron and a simpler binary ferritic alloy with 5% of chromium to have some simple microstructure to compare it with. Okay, today I'm going to talk mostly about those first 4 materials, and the pure iron, the last one, hasn't been evaluated yet. So the materials were made into 3 batches, and the first batch went here, and it was irradiated by neutrons at the LVR-15 reactor. So the DPA is around 0.12 DPA, so again we are at early stages of radiation damage. And here you have some details regarding the neutron energies and the fluencies that were used. And the second table summarizes the irradiation cycles, because the samples went through 5 irradiation cycles. Each had a little bit different temperature, but on average it was around 260 degrees. And also each one lasted a different amount of time, but the total amount of time was about 101 effective days. Here are also some details if anyone's interested about one of the cycles. Here you have also the reactor core configuration, which you already saw in the presentation of Mark Scholtes. Just for you to know, in this cycle the samples were at this position of the reactor. Here you have also some reactor power evolution over the time. Then the second 2 batches of the materials were sent to Faculty of Material Science and Technology in Trnava, which is also part of the Slovak University of Technology. Here they were implanted with hydrogen at 2 different temperatures. One batch was at room temperature and the second one at 300 degrees. So we have some temperature comparison with the neutron irradiation. As you can see, the DPA is a little bit lower because when we did some calculations regarding the implantation and the damage profiles, there were some concerns regarding the blistering of the sample. So it's a little bit lower than the DPA of the neutron irradiation, but still somehow comparable. And as you can see, it only lasted about 16 hours. So this is one advantage of the proton implantation. The experiment takes much less time. And the energy of protons was 5 MeV. Okay, and what we used to study the samples was the positron emission spectroscopy at our laboratory. Just to tell you some simple principle for those who have no idea what this technique is about. The principle is in implanting a specimen with positrons where they can find an electron they can annihilate with. And when you have some defects present in the material, such as vacancies, they act as potential wells for those positrons, which on average prolongs their lifetime in the sample. And we can measure this lifetime, and based on this, we can qualify and quantify the defects that are present. That's one method that is being used. It's called lifetime spectroscopy. The other one is a Doppler spectroscopy, where we measure the non-zero momentum of the annihilating pair. And that causes a broadening of the photopeak in the energy spectrum, and based on the analysis of the spectrum we can also tell something about the defects that are present and the chemical composition of the annihilating sites. Here we have also a spectrum of the lifetime spectroscopy, and this is a setup we use in our lab, but it's not so important right now. So, okay. Some results that may be interesting. So here we have comparison of those 3 FM steels, so T91 SIB and ODS Eurofer. One of the great things we obtain from the positron annihilation is the defect concentration. So here on this figure we have some comparison of relative vacancy concentrations. Regarding the vacancies, as we are in the early stages of radiation damage, we assume just small vacancy clusters to be present. So we are talking about mono and D vacancies. And we have here the comparison of those 3 materials and also those 3 irradiation environments. So one of the things that is basically obvious, but we confirmed it, is that the ODS steel shows the highest stability after irradiation. As you can see, there is only a slight increase at the low temperature implantation in the concentration compared to the other samples. And at the high temperature irradiations, there is even a decrease in concentration. So that means the recombination of defects prevails the production of them. We can also see it on this figure. Here we compare something we call an S parameter, which is parameter coming from the Doppler spectroscopy. It basically says something about how many positrons annihilate with valence electrons. That says something about the defects basically that are present. And here we have a parameter called MLT, which means mean lifetime of the positrons, and that gives us some general idea about how much the material is damaged. So as you can see, the points of ODS are pretty closely packed together in comparison with the T91 or SIM, where we go from around 130 picoseconds of MLT to almost 170 picoseconds of MLT. When we compare the conditions, as you can see, the most profound increase is at the low temperature implantation. So here, what we think is probably going on is that the hydrogen fills the vacancies that are present and basically stabilize them, because there is no more room from an interstitial to come and annihilate the defect. So yes, so basically the damage is most profound at this condition. At high temperature implantation, we see decrease in all those materials. So here the recombination prevails production. Because of the high temperature, the defects and also the hydrogen is very mobile. So here we have basically an annealed sample. And the neutron irradiation, well, there is some increase in the T91 and SIM. Since the temperatures are comparable with the proton implantation, we could say it should be comparable, but of course the interaction of protons and neutrons with atoms of the microstructure is a little bit different, so here we can actually see the difference. Okay, some more figures. So what we have here is some comparison of the S parameter I already talked about and W parameter. W parameter tells us something about positrons that annihilate with core electrons. So it can tell us something about the chemistry of the annihilation site. What I want to point out that may be interesting, when you have a linear dependence between the conditions, that basically means the defects in the samples the type of defect doesn't change. But here in the T91 we can see that for neutron irradiation it doesn't align with the linear function, and we also saw that from the lifetime analysis that there was change in the defect type, where the reference sample and the proton implanted samples showed some smaller vacancies, so monovacancies or divacancies. The neutron irradiated samples had a larger cluster of vacancies, so around 4 or 5 vacancies. Okay, in the SIM they are pretty much aligned, and as you again can see, the ODS are closely packed together, so that also says us something about the radiation stability of the ODS, given by the presence of oxide particles that can act as defect sinks and annihilation sites for the newly created defects. Below we have something called momentum curves. Those basically show us how many annihilations happen at a given momentum, a reference to some sample. Here all of them are reference to pure iron. Again, what is interesting that the ODS, basically all the conditions follow one curve, so again, radiation stability. Here in the SIM, we can see a pretty big dip at the low temperature implantations. That basically tells that there is a lot of damage going on compared to the others, so a lot of defects that are present. Okay, continuing to the ferritic chromium alloy, this is again a comparison between those three environments. The trend is pretty much similar, so the biggest increase is at the proton implantation. And well, one of the conclusions we came up, since we are comparing proton implantation with with fission neutrons, damage caused by fission neutrons, maybe in terms of the vacancy defect concentration and early stages of radiation damage, the proton implantation could be used to simulate some fusion neutron damage, since the fusion neutrons will have higher energies, should cause more damage in terms of more defects that should be present in the samples. Yeah, again, the SW figure shows us that the type of defect doesn't change very much. And yes, what is interesting at the momentum curve, that here the neutron irradiated sample pretty much follows the reference sample. So yeah, at the neutron, as you can also see here, it doesn't change very much. Then we took the ferritic alloy and compared it with pure iron, just the neutron irradiated samples. Again, not so surprising, but the alloy behaves more stably than the iron because it's a more complex microstructure, so there should be some objects that can enhance recombination, such as chromium precipitates that can act as defect sinks. We also did some momentum curve analysis. Again, here we have it referenced to the reference sample of pure iron. So as you can see, the ferritic alloy, both the reference sample and the irradiated one follow pretty much the same curve, whereas the irradiated iron behaves differently. And this one is compared with the pure chromium to see if we can observe some contribution from those chromium precipitates where the positrons could annihilate in. So here the dip in the curve in the similar region of momentums basically confirms us that there is a lot of positrons annihilating with chromium electrons basically, but it's not a direct confirmation of that there are the chromium precipitates present, so there are also some other plans to confirm that. And last thing I want to mention, this was done in preparation for another experiment. So that's a follow-up project on COMA called RIDER. It's basically a PhD project given to me by our faculty. And here we took the neutron irradiated samples of the ferritic alloys and the pure iron from the neutron irradiation, and we decided to implant them with hydrogen to see interaction between the quasi-inherent defects from the neutron irradiation with the newly formed defects from the proton implantation. So the experiment before, we did it to actually evaluate the number of vacancies, the concentration of vacancies in the sample. So we could design specific hydrogen fluencies to follow a certain hydrogen to vacancy ratio. The ratios are here, so we have 1/2 of hydrogen to 1 pair of vacancies, then 1:1 and 2:1. And these are just some preliminary results of just the ferritic alloy. But as you can see, for example, the vacancy concentration between those three fluencies, we see a decrease at the second fluence, which, well, we could assume that it should go higher because we introduce more damage to the material, but it actually decreases. Also, when we look at the S parameter, it slightly decreases in comparison with the first implantation. And here, one of the possible explanations is that at this point, the vacancies become so filled with hydrogen, there is no more room for positrons to be trapped in. So the material actually looks less damaged to us. It creates basically an illusion. And then at the third implantation, we see a profound increase in the concentration. At this point, basically the vacancies become so oversaturated with hydrogen, they release the hydrogen and create even more large agglomerations of defects. So this mechanism needs to be more studied, which is also the next part of this research. So just some quick conclusions. We saw some influence of temperature on recombination, and also we suggested vacancy stabilization by hydrogen in case of low temperature proton implantation. We suggested that the low temperature implantation may be used to simulate fusion relevant neutrons in terms of vacancy production in those early stages of radiation damage. And yes, as I told, at certain implantation fluencies, the vacancy clusters may be completely filled with hydrogen, resulting in less damaged material, which sounds like, okay, why do we care? But this is one of the problems that the positron community deals with. So, okay, thank you for your attention, and now I'm open to any questions that you may have.
Thank
Thank you, Sofia, for a very interesting presentation. I really like the evolution of your project from mosquito to the rider. Sounds really nice. So are there any questions or comments? On the upper level, I need to stretch my legs. Okay, if not, thank you very much. I would like to thank to all the presenters and as well as to all of you who stayed here till the very end. Basically, this part of the core conference should show you what is CISR or Large Research Infrastructure CISR about it, as well as you have seen that this infrastructure is helping us to support the collaboration with the universities, namely with the Slovak technical universities, Czech technical universities, but also with other research institutes like UKEA or CA from France. So thank you very much for your attention. I don't know if Otakar wants to say something more, but for those who are joining the tour, technical tour, please enjoy it. And if you will be at the reactor, look at the space, it's not so much. Thank you.